Previously on What is Probability? So last time we talked about relationships between variables, and sometimes we have causation and sometimes we have correlation. Causation, very hard to prove, very difficult to prove that one thing causes another, but pretty easy to prove that two things are related. And because it's so easy to prove that two things are related, or correlation, we have a nice scale all about correlation, a beautiful spectrum. We're going to start over here on the right where we've got a positive strong correlation. As one goes up, the other goes up. That would be like homework versus grade, everything nice, tight to the line. The linear progression is a beautiful representation of this data, and it will be very good for our guesses like interpolation, extrapolation. Then we've got positive moderate correlation. In this case, our bubbles are a little bit further away from the line, but still, as one goes up, the other one is also brought up. It's a very positive correlation. In the middle, we have no correlation at all. This would be birthday versus grade. In this case, there is no relationship, and our R is 0. Zero correlation here. Then we have a negative moderate correlation. The bubble's not exactly on the line because, of course, there will be some people who are more likely to be outliers depending on the video game and depending on their original grades. And then, of course, we have negative strong correlation. Notice in both the negative cases, as one goes up, the other one is brought down. That is what a negative relationship means. Strong negative relationship means it's tight to the line. A moderate correlation means it's a little bit further away from the line, but it's still a definite trend. What is probability? Episode 10, Linear and Exponential Patterns. Illustrated and narrated by Izzo. Okay, so we've got our graph paper, and I'm going to do day on this axis. And these points are actually legitimate. I looked up the data and plotted the real life data. I did not make this stuff up. For once, this is real life right here, on black and white-ish. But if we notice, it's not so linear. This is the coronavirus in the USA. These are the number of new cases that pop up each day. But these are the days from before the shutdown, from before the social distancing. So from February 21st on the left all the way to March 9th on the right, these are the actual number of new cases that popped up in the USA. Before social distancing, before shutdown, before any of that. This is why we did the shutdown. This is why people started working from home. This is why we started social distancing. Because people saw this progression and said, oh, that's not good. That's not good at all. Notice, linear means line. So if we try to fit a line graph to this, it doesn't really fit the dots. I mean, it's sort of a moderate, but it doesn't really fit what the dots are telling us. In this case, it's not a linear progression. So what we do is we get rid of the line and we fit something that is actually a better representation of the data. In this case, it's an exponential graph. If we look at the swoop of an exponential graph, that fits the coronavirus statistics very, very well, which is why when you see any news on the coronavirus, a lot of times they will talk about the exponential growth rate and flattening that curve so it doesn't spike up so quickly. Because if we look at that spike, it don't look so good for America. It look pretty bad. We gotta be careful. That is why we started shutting down. and that is why we started social distancing. Because statisticians took the data, plotted the real life data on a graph, and noticed that we were increasing and increasing way too rapidly, and our hospitals wouldn't be able to handle that. Notice, because we have linear graphs and we have exponential graphs, that opens up a whole lot of possibilities. So when we have things like Grandma's Garden, that is a beautiful linear graph. When we have stuff like the coronavirus or zombies, that's an exponential graph. But we've talked about a lot of different graphs in Algebra 1. We've talked about linear graphs. We've also talked about absolute value graphs. We've also talked about quadratic or parabolic graphs. We've talked about cubic graphs, square root graphs, and most recently our exponential graphs. These are all different types of graphs that could be matching data points depending on what our statistics is about. Certain statistics are very linear, like if you're talking about rent. Rent stays the same, particularly if you're on a fixed monthly rent. It will stay the same each month, so the rate goes up each month of how much you have paid to your landlord. That is a nice, steady, linear graph. Whereas coronavirus has that swooping action, which is exponential. If we play sports like football or basketball, anytime you throw an object, that becomes projectile motion, and that is all about quadratic progression. So linear, quadratic, and exponential are the three most important graphs on here. For the regions, we care most about linear and exponential graphs. So let's take a look. What statisticians normally do is they try and guess the pattern, and sometimes they might try more than one pattern. If we look, we've got a whole bunch of different data sets. In each of these graphs, the points are arranged in very different variations of each other. They're the same number of points, but they're organized differently. In the first one, it looks more like a linear progression, so statisticians would fit a line graph to it, a nice linear regression line to it. For the next one, this one's an exponential, like a zombies game. This is what would happen if we have an exponential regression, which is actually an option in your calculator. You could do a linear regression, you could also do an exponential regression. And the last one, if we tried to do a linear regression, it would be zero correlation. There would be no correlation because there looks like there's no relationship. However, if we fit a nice parabola to this, like the bouncing of a ball, if we throw the ball down and it bounces up, that is a nice quadratic regression line. And it follows a nice, easy pattern. There is a great relationship there, but it can only be captured by a quadratic regression. It can't be captured by a linear or an exponential regression line. So that is our parabola, or our quadratic regression. With our time together here, we have talked about what happens when we draw cards, when we play dice games and draw multiple cards, what happens when we do statistics or try and find parameters of certain populations, like with your quiz scores, what happens with weighted averages or curved scores. Episode 5 was all about how to choose the right sample. If you can't do the entire population, how do we get an unbiased, good sample out of something and avoid all of the biases? Episode 6 was what happens after we have the sample and how we do an experiment or an observational study. Episode 7 was a lot about picking on the poor Pennsylvanians, and we picked on a lot of Floridians too. I feel bad about that. We were very, very cruel to those people. But what it did was we talked about the whole cycle, how we wanted a population, how we wanted information from that population. So we had to pull a sample, do statistics on that sample so we could learn about the population. Then we talked about bivariate statistics, what happens when we don't want just one piece of information about the population, but we want to know about the growth rate or decay on the population, what is happening to the population over time, or how two variables are related. We then seriously discussed the relationships on the variables, what is causation versus what is correlation, and the spectrum that we need to talk about with correlation, and how related two variables can be, and if it's a positive relationship or a negative relationship. And then finally today, we have talked about the different types of patterns and how sometimes it's not a linear pattern that we are seeing in this bivariate statistics. We are seeing more of a quadratic or an exponential pattern, and how to tell the difference between those. So the big question after all of this information is, how will this help us in real life? Stay tuned for next week as we review what we have done and actually talk to people about how they use this in real life. The end.